In this video, we're going to investigate 10.2G and I. First, 10.2G says let's perform a significance test to compare two means. So here's the base information that we want to know. A significance test for the two means, here's our title, would be a two-sample t-test for the difference between means. Our hypothesis is always going to be the null hypothesis of no difference. You can write one of two ways, either showing it this way or do your algebra to bring m of 2 over, and you could say m of 1 equals m of 2. And then you'll state your corresponding alternative hypothesis that you want. The test statistic here is very similar to that used in the confidence interval. Remember, unlike the proportions, it's different for the test, but for the means it's the same, where we're seeing the difference in the two statistics, our hypothesis difference, and then our standard deviation of the combined two variables. So once you've determined which alternative hypothesis that you want, you do have to check your conditions. And they are the exact same thing as they were for the confidence interval. So first we're going to start by checking for randomness. Is the sample of N1 from population 1 and the sample of N2 from population 2, were they done randomly, or was it a randomized experiment for both of the two samples? For independence, again, both samples or groups need to be independent. If you are sampling without replacement, check the 10% condition for both. And then for normalcy, remember there's different levels of normalcy though. If they are pulling from a population that are normal, then we know our samples are normal or approximately normal. If they meet the central limit theorem, where each sample is greater than or equal to 30, then we know by that the samples are approximately normal. Or if we get smaller than that, the two other extremes are, keep in mind, if you are less than 30 but up to 15 basically, you do have to graph it out. You're looking for no extreme outliers or strong skewness. Really just the extreme level on here. Anything less than 15, you need to graph it out and look for no outliers or skewness in this case. So let's look at this stronger picker-upper example. In commercials for Bounty paper towels, the manufacturer claims they are the quicker picker-upper. The question is, are they the stronger picker-upper? Well, two AP Stat students, Wesley and Maverick, decided to find out. They selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held two opposite edges of the paper towel, and counted how many quarters each paper towel could hold until it was ripped. And they recorded the approximate data that you're going to see in your packet. So you see 30 pieces of data for Bounty, 30 for the generic, and again basically it talks about how many quarters that each of them could hold. Here they want us to actually describe the distribution. So to describe this distribution, they basically are asking us for socks. Now here we also have the actual box plot for each of the outcomes in terms of how many quarters it took. Let's describe the distribution in this case. Now what we could say is that both distributions are roughly symmetric, but the generic brand has 2 high outliers that we see. And folks, remember, if you put this data in your calculator under list 1, you can do a stat plot and it'll actually do the modified box plot for you, which computes the outliers. So I highly recommend doing that because then you don't even have to do the outlier test. Now, in terms of the center, what do we see? The center of the Bounty distribution is much higher than the center of the generic distribution. We clearly see that in the means. Now, although the range of each distribution is roughly the same, if you compute the range for max minus min of both, it's about the same. The interquartile range for the Bounty distribution is quite a bit larger. Remember, the box itself shows us the interquartile range. Now here they also say the box plots display the results of the experiment. Based only on the box plots, discuss whether or not you think the mean for Bounty is significantly higher than the mean for the generic. Now remember, the mean, if it's skewed, the mean is pulled in the direction of the skewness. But we said both of them are roughly symmetric. So what could we say about their means? Because the box plots only show the medians. Well, what we could say is, since their centers are so far apart and there is almost overlap in the two distributions, the Bounty mean is almost certainly to be significantly higher than the generic mean. If the means were really the same, it would be virtually impossible to get such little overlap that we actually see. Well, let's do a test for it. It says here we have the data, which we already have. Is there convincing evidence that the wet Bounty paper towels can hold more weight on average than the generic paper towels? So let's define our variables and then go ahead and state our hypothesis. So the variables by definition here is I'm going to have M of B and M of G, the mean weight of quarters for Bounty and that for generic. Our null hypothesis is that there's going to be no difference between the difference. So M of B minus M of G is 0. But what do we think is really the case? Well, we think if Bounty minus generic is actually going to be higher. So what we can say for our hypothesis is this. The alternative, M of B minus M of G, is greater than 0. And I'm going to choose a 5% significance level. For the plan portion, let's talk about what we're choosing. We are choosing to conduct a 2-sample t-test for the difference of these means. Was randomness taken care of? In this case, the students used a random sample of paper towels from each brand, so we're good on that. How about for normalcy? The normalcy, even though there were 2 outliers in the generic distribution, both are reasonably symmetric and the sample sizes are at least 30, so it's safe to use the T procedures. In independence on this, samples were selected independently, and it's reasonably to say that there were at least 300 paper towels of each brand in the population that we could have chosen from. So we are actually good with that. The do portion, let's look both at what I would manually write down and what if I did it on the calculator. So the manual information, we do want to have the mean and standard deviations listed, which we do. That is going to help us compute the test statistic. Now, a little bit of this got caught off, but what we have here is the mean of Bounty minus generic, and it's going to be minus, we think the difference is 0. And then that's all going to be over our standard deviation. So this is 6.30 squared, and these are both sample sizes of 30 on the bottom. And that will give us our test statistic in this case, which is going to come back at the number of, it's 17.65. Probably one of the highest statistics I've ever seen for computing probabilities. All right, let's just do this by hand though. Remember, for conservative degrees of freedom, we do have to choose our degrees of freedom is sample size minus 1, which is 29. Now, when I show you the calculator, you're going to notice the degrees of freedom on the calculator are incredibly different here. It will be 57.8. The p-value is going to be 0 on this, but folks, think about it. When you do this, we're going to have a test statistic of 17. I need to go higher. So remember, if we use the calculator, we're going to do a t-CDF, not normal anymore, it's t-CDF. I want to have from 17.65 up to 999. They're going to ask you in their calculator for conservative degrees of freedom, and I'm going to type 29. That will give us a p-value of approximately 0. Now, if you use the calculator, and again, of course, I recommend it, here's the calculator screens. We're going to go to Stat Tests, and we're going to choose the 2-sample t-test. You can either input the raw data in list 1 and list 2, or your statistics. The stats, again, are going to the mean and standard deviation and sample size of 1, that of 2. Pick the actual hypothesis that we're doing. We're saying greater than. In pooled, obviously say no. When you hit calculate, here's what you're going to get. Obviously, I would write down, just what we always have talked about, let's write down the test statistic of the 17.65, which we saw here. This is the p-value. Folks, it's scientific notation of negative 25 zeros. So you move the decimal place 25 to the left, obviously that is going to be a p-value of a big old 0. Degrees of freedom, you must write down this degrees of freedom. If you use the calculator, again, do not state the conservative degrees of freedom of 29. Just give the calculator's degrees of freedom. And then I do recommend writing down the mean and standard deviations. If you scroll down, you will get that for all the information. Let's make our conclusion. So in this case, P is less than 0.05, so we'll reject H sub O. And I'm going to put 0 is less than 0.05 to show my math. If we reject H sub O, we can therefore conclude H sub A. So I'm just going to say there is convincing evidence that wet Bounty paper towels can hold more weight on average than generic paper towels. It's a great review question from Chapter 8. Interpret the p-value in context. So remember what p-value means again. It is the probability that our statistic happened given that H sub O was true. That's what the p-value. So I will literally just go in here and kind of walk myself through this, how it's written out in context, keeping in mind the p-value is 0. So I could say the probability that the outcome of our two statistics or something more extreme actually happened, given that the mean difference in our paper towels is truly 0, has a probability of 0, which is so unlikely. Here's maybe a little better way to say it, though, if you're going to be more thoughtful. Since the p-value is approximately 0, it's almost impossible to get a difference in the means of at least 29.5 quarters by random chance, assuming the two brands of paper towel can hold the same amount of weight when wet. So don't forget how to interpret the p-value. We need to take some time now and just talk about using the T procedures wisely in other conditions. So we've talked about this before, but it's important to highlight. If you have a sample size less than 15, remember you have to graph out the data, and the data has to appear approximately close to normal, and we don't want to see any clear skewness or outliers present. For the sample size to be at least 15 in this case, don't use in the presence of strong skewness or outliers. So this gives you a little bit more wiggle room as the sample size gets larger. And then the last one, for large samples, if we're greater than or equal to 30, that's fine, even if we have skewed distributions for our population. Now remember when we were doing the difference of the sample means, either the confidence intervals or the tests, on the calculator there was actually an option for a pooled. I just want to highlight a few things about that. The first is that it assumes two populations have the same variance. And so what it does, if it's kind of being conservative in its own right, if we use the calculator feature for that, it would give a higher degree of freedom, which is going to give us a narrower confidence interval and a smaller p-value. So that's kind of a benefit to it if we were to use that method. What the pooled estimator of our sigma squared or our variance is, you might hear pooled estimator. It's the weighted average of the standard deviations based on the degrees of freedom. And there's actually a formula for the pooled estimator. It is this right here. It is on the AP formula sheet. But absolutely, completely ignore this formula. You will never have to reference this formula at any time, either in homework or on the true AP exam. Just highlights here, do not use that pooled button for the means. It's only for the pooled proportion for the test of the difference of two proportions, not the confidence intervals. Anything pooled for the means can absolutely be ignored. So what if you were asked, okay, fine, we don't pool for the means, but why do we pool a two-sample test for the difference in proportions? That is, why do we do this? Here's what I'm going to tell you. We don't need to know it for the test. Do not worry about that. Just remember you have to do it. It's nothing that you're going to have to be asked any further details about. Okay, another concept you might be wondering. Should we use a two-sample T procedure if we have paired data? Remember we talked earlier about matched pairs. When can two sets of data be combined as their differences just to look at one set of data? What we're going to dive a little bit more into is talking about, should we keep something as a two-sample test, or do we combine it and actually look at the differences? If you combine it and look at the differences, do know that you would not use the two-sample T procedure. So, for example, if the same subject received two treatments, again, maybe I'm not feeling well, so they give me an aspirin. Maybe later on I'm not feeling well, they give me a placebo. If I want to see, did that aspirin help, I could look at the difference of those two data sets. In that case, it's paired. So I would just do a one sample, or in that case, a paired data test, which works like the one sample and not the two sample. In those cases, you do just group the data and use a one sample T procedure. You would not use the two sample procedure. Now let's quickly look at 10.2i. We're going to interpret the results of inference procedure in a randomized experiment. We're just going to look at this one example. So here it says, suppose you're designing an experiment to determine if students perform better on tests when they are not distracted, such as a teacher talking on the phone. You have access to 2 classrooms and 30 volunteers that are willing to participate in your experiment. Design an experiment so that a 2-sample t-test would be appropriate. Why should we keep it as 2 separate samples, and why wouldn't we group it as a paired example? Okay, so we're going to design this experiment. How would we do it? Great review of Chapter 4. Knowing that we have 30 volunteers, maybe what we would do is on 15 index cards, write A, and on the other 15, write B. Shuffle the cards in a hat and hand them out randomly to the 30 volunteers. Okay? Then what we would do is all subjects would take the same reading comprehensive test. So all 30 people start with the same test. Then what I would do is say subjects that receive the A card will go into the classroom with no distractions, and subjects who receive the B card will go to the classroom that will have a proctor talking on the phone during a test. And they will all take the same second test. Now, after that's done, at the end of the experiment, compare the mean score for the subjects in room A and the mean score for subjects in room B. That's the way you could design this study and keep it as 2 separate samples. What if I wanted to make it paired data and I just wanted to do a 1-sample t-test for it? What would be a good way to design that? Well, basically, I want to have 1 subject, but that 1 subject is going to get both of the treatments. So we have to make the person get both treatments of quiet and distracted room. So let's do this. Let's use the same procedures in A to divide the subject into the 2 rooms and give them the same comprehensive reading test. However, before they start the test, 1 room will be distraction-free and the other will have a proctor talking on the phone. So the first test they take, half the group will be in a quiet environment, the other will not. Okay, then let's take a short break and give all 30 subjects a similar reading comprehensive test, a second one, but the distraction is going to go into the opposite room. So they're both taking test 2, but those that weren't distracted before will now be distracted and vice versa. At the end of the experiment, calculate the difference in the 2 reading comprehensive scores for each subject and compare the mean difference to 0. So I'll have 1 set of data now of all the differences of the students. Well, knowing those 2 methods, here's a question. Which experimental design is actually better for this and why? Well, it's probably going to be better to use the design in Part B. Use the matched pairs. Since it eliminates an important source of variability, one's reading comprehension of all the individual subjects. So to control for one's variability to learn, having the same subject do kind of the both treatments will actually take care of that, and it should not be impacted or be a confounding variable in your experiment.